So far, we've talked a lot about elements. So we've gone through what does an atom look like, we've gone through how does it have different numbers of neutrons, we've talked about isotopes, we've talked about ions, we've talked about lots of stuff. But what we're going to do today is actually talk about when elements combine together. You see, what makes chemistry so interesting is that you don't just have those atoms, you have your 92 atoms to start, but they can combine together in all sorts of combinations. And every time they do combine together and make what we would call a compound, that compound ends up having totally different properties from the substances that we started with. And there are lots of different types of compounds. So what you end up getting is a huge variety of materials that the universe can be made of. And so what we're going to look at today is just one simple type of compound, and that is what we would call an ionic compound. So the first thing we should probably do is actually talk about what it means to have a compound. You see, a compound is when we have two or more elements bonded together. Now, you may be wondering, what do I mean by bonded? Well, bonded is a chemistry term meaning they are actually stuck to each other and will not go away. Basically, when a bond forms, electrons are used in order to actually connect the atoms together. And this can happen in multiple different ways. So electrons can connect through the exchange of electrons. Exchange of electrons will actually result in things having charges, which will make them actually stick to each other. You can also have things that share electrons. And so by sharing electrons, basically they're stuck to each other because they end up like having orbitals connected together with each other. These are the two major classes of compounds. If something exchanges electrons or shares electrons, they create our two different types of compounds. The exchange of electrons creates what we would call an ionic compound, a compound made of ions with charges. The sharing of electrons results in what we would call a covalent compound. And if you think back to what valence or valent means, it means the outside electrons. Co means to share, so a covalent compound, they are sharing their outside electrons. These are the two major classes of compounds. Ionic compounds and covalent compounds are extremely different. In fact, they're so different that when you really get to know chemistry, you can pick them out just by looking at them without even knowing what the atoms are. I know that my computer is mostly made out of covalent compounds. I know that the air I breathe, covalent compounds. I know a lot of the baking materials that I use, like salt and baking soda and baking powder, those are ionic compounds. And I just know this because of the properties that they have. So we're here to talk about ionic compounds. Let's figure out what they actually are. Okay, so an ionic compound is when we have two oppositely charged particles, and those oppositely charged particles are attracted to each other. Essentially, you get a positive and you get a negative. And when you have positives and negatives, opposite charges attract. So those two oppositely charged things are literally just going to stick to each other. So an ionic compound is made of those two things that actually stick together. An ionic compound is usually quite easy to find because it is made of both a metal and a non-metal connected to each other. It is possible as well that it contains something that is called a polyatomic ion, which you can probably guess what it is based on the name. Poly, many. Atomic, atom. Ion has a charge. Many atoms that have a charge. Now, we'll see these a little bit later, but I wanted to demonstrate what an ionic compound actually looks like and how they actually form. Think back to when we talked about ions. We talked about how you can have things that are cations that have lost electrons and gained a positive charge. You can also have anions, things that have gained electrons and therefore have a negative charge. But where did they get the extra electrons? Where did cations lose them to? Where did anions gain them from? It's not like electrons are just floating around in the air doing whatever they want. They're always bound to an atom. So that means if you lose an electron, you actually have to lose it to another atom. If you gain an electron, you actually have to gain it from another atom. So let's take a look at how that would happen. Let's take a look at a quite simple ionic compound. Let's say we are going to take a look at lithium fluoride. So that means lithium bonded to fluorine. Now I know just by looking at this that it has to be ionic. How do I know that? Metal, non-metal. The two are stuck together. So what's going to happen here is we're going to have a lithium atom. And think back to when we drew our atoms. This is going to have 3 protons, 4 neutrons, 3 electrons. So I'm going to draw my atom with my nucleus. It's going to have 3 protons, 4 neutrons. It's going to have 2 electrons in the first orbital. It needs 1 electron in its second orbital to get its 3 electrons. Now I'm also going to have fluorine. And fluorine is going to have 9 protons, 10 neutrons, 9 electrons. So I'm going to have my 9 protons, 10 neutrons in the nucleus. I'm going to have my 2 electrons in the first orbital. And then in my second orbital, I need to have 7 electrons. 6, 7. Okay, so that gives me my 9 electrons in total. Now, there's something important to understand in chemistry. Things are more stable if their valence shell, their outside shell or outside orbital, is full of electrons. In these 2 atoms, you can see that it only has 1 electron in its outside shell that could hold up to 8. And fluorine is 1 short of having a full valence shell. These 2 molecules are quite unstable, quite reactive, because they don't want to exist this way. They actually want to get to the point where they have full valence shells. So the easiest way for them to do this is for lithium to actually lose an electron. And when it loses that electron, it's going to go to the fluorine. So now let's think about what's happening. Fluorine now has 10 electrons. So fluorine now has a -1 charge. Lithium gave away its valence electron. So it no longer has that second orbital. It also now has 2 valence electrons. So lithium has a positive charge. When you end up having this, a positive and a negative, the 2 are attracted to each other. And they're actually literally going to stick together, kind of like 2 little magnets. And so you have lithium, you have fluorine sticking together because of the exchange of electrons. This exchange of electrons is what creates ionic compounds. And it always happens because you have substances that are trying to reach a full valence shell. That means if you have something like calcium that's in the second column and has 2 valence electrons, it actually wants to lose its 2 valence electrons. And if you have something that has maybe 3 short of a full valence shell, like nitrogen or phosphorus, they're going to want to gain 3 electrons. There's an important thing though. In an ionic compound, the total sum of charges must add up to be 0. That means you can never have an ionic compound that actually has its own charge, but it is made of charged things. So let's take a look at some examples. Here I have some different examples of ionic compounds. I have sodium chloride, barium chloride, calcium sulfide, and iron oxide. Now, what I wanted to go through is the fact that you notice none of these have a little charge in the top right-hand corner. And that's because an ionic compound has to add up to have a charge of 0. So we can take a look at the ions that it is made of and make sure that it's actually going to add up to 0. So you see sodium has a charge of +1 as an ion. How did I know that? Well, I know that because of the periodic table. Sodium is in the first column on the periodic table, so it's going to have a charge of +1. Chlorine, the other substance, is in the second last column, column 17, and everything there has a charge of -1. So that means Cl is going to have a charge of -1. When those combine together, you have +1, -1 for a sum of 0. Over here, you see we have something a little bit different. There is a subscript written next to Cl. What this actually tells me is that there are 2 chlorine atoms. So why are there 2 chlorine atoms? Well, barium from your periodic table is in the second column, so it has a charge of +2. Chlorine has a charge of -1. So in order for this to add up to 0, I actually need 2 chlorines, because then my sum comes out to be 0. You see, because of the +2 charge, there needs to be 2 -1s to balance it out. So there are 2 chlorines actually sticking to every 1 barium. Now over here we have calcium sulfide. Calcium has a charge of +2, and sulfide has a charge of -2. +2 minus 2 adds up to be a sum of 0. And because they end up having the same charges but with opposite signs, you don't need any subscript because you don't need to add together any extra atoms. All right, let's take a look at this example. In this example, we have iron and we have oxygen. Now, I wanted to take a look at our periodic table for this. So take out your periodic table, take a look, and this is what you should see. In the box for iron, you should notice that it actually has more than 1 charge. You see, iron is what we call multivalent, and if you zoom out and take a look, you're actually going to find that there are many multivalent metals. Essentially from column 3 all the way to column 12, and even a few of these ones that are under the staircase, those make up what we call the multivalent metals. Typically these ones, they would be your transition metals. From column 3 to column 12 are what we call the transition metals. But underneath, some of the poor metals, the ones underneath the staircase, do tend to have this multivalent character as well. So what are we dealing with here in this? Well, oxygen is not multivalent. Oxygen is always a -2. And you have 3 of them. So 3 times -2 is a total of -6. The iron has to have a charge that is going to equal out to be +6 because it has to add up to be 0. So what charge does it actually have? Well, we don't know the charge that it has, but we know there are 2 of them. And to have a charge, or to end up with a total charge of +6, it means it had to have a charge of +3. So this is what we would call iron 3 because of its charge of +3. So sometimes you need to actually be able to take a look at those charges and figure out how they balance out in order to identify what the charge of multivalent metals might be. Now, the other thing I mentioned is there are also things that we call polyatomic ions, many atoms with a charge. So let's take a look at a few examples of that. Here I have CaCO3. So I know, mostly because I have kind of memorized my polyatomic ions, that CO3 is a polyatomic ion. The reason that I know this all has to do with a large chart. There is actually a table of all of the polyatomic ions that you can use to help you figure out what they are. But the other way that I know this is I have a metal. And so calcium as a metal in a compound has to have a charge of +2. What that means is this whole other thing, CO3, has to have a charge of -2. CO3 is a polyatomic ion called carbonate. And you can actually figure out by reading the names that certain things have polyatomic ions. Polyatomic ions always end with 8, ite. Those are really the 2 endings that you would see after an ion to identify that it's polyatomic. So you might have something like sulfate, or sulfite, or nitrate, or nitrite. All of those things, because they have these endings, are polyatomic. There are 2 exceptions. Cyanide ends with IDE, but is carbon and nitrogen with a -1 charge. The other exception is ammonium, which is NH4 with a +1 charge. And it's actually the only positively charged polyatomic ion that you'll probably ever see. Now, I mentioned that you can also pick out what an ionic compound looks like. I know that all ionic compounds are going to be solids at room temperature. And not just that, they're almost always going to be crystalline solids unless they have been powderized. How do I know this? Well, it all has to do with forces. You see, the charge of each of those ions attracting each other is immense. It is a huge amount of attraction. And so it's very, very hard to pull those things apart and requires a lot of energy. What that means is an ionic compound will be solid at room temperature because it's hard to get them pulled apart. There's just not enough energy at room temperature for them to be taken apart from each other and exist as a liquid or a gas. The other thing is, because of that attraction and the way that they work kind of like tiny little magnets, is they tend to form crystal structures when they are solids. You see, let's say we have something like sodium chloride. Sodium chloride, or salt as you probably know it better, is a crystalline solid. It has sodium ions that are positive, but stuck to those sodium ions are chlorine ions that are negative. And they actually end up packing together into a very specific pattern. That really specific pattern actually repeats until they become large enough structures that we can physically see what that looks like. So ionic compounds actually tend to pack together into crystal structures. What this means is you can actually figure out the crystal shape of something based on the physical shape of the actual crystal. So if a crystal turns out to be a cube, then it means that the atoms are packing together in cubes. If the crystal packed together in a hexagon, then the atoms are packing together as hexagons. So whatever shape the crystal is, it actually shows you the shape of the ionic atoms actually sticking to each other. The other thing we should know about ionic substances is that they tend to have extremely high melting and boiling points. This is because that high amount of attraction, they don't want to disassemble from each other. So they actually want to stay solid. Most of the time, an ionic compound will tend to melt in the range of 700 to 1,000 degrees, and they tend to turn into gases around 2,000 to 3,000 degrees Celsius. Now, and so it depends on each substance. Each substance is a little bit different, but we're talking about extremely high melting and boiling points when it comes to ionic substances. Now, despite the high amount of attraction, there is one substance that can actually disassemble an ionic substance quite easily, and that's water. You see, when you have your ionic substance, water has a special property to it that water, or H2O, is also itself kind of like a tiny little magnet. You see, water has a slightly positive side and a slightly negative side. So it ends up having kind of like little poles or little charges on each end of that molecule. So what ends up happening is if you have something that is positive and packed together in a crystal structure, then the little negative oxygens in water can actually attract to it. And what will end up happening is the water will end up surrounding that ionic substance. It can then actually pull it away from the lattice completely and separate it out into the solution. So you would end up with your positively charged ion totally surrounded by waters and separating it out into the crystal, into the solution, away from the crystal. The other thing that can happen here is because water also has slightly positive sides, it can do the same thing by taking its slightly positive hydrogens and aligning them around a negatively charged ion and then pulling them away from the crystal lattice so that you end up with these negatively charged ions totally surrounded by positively charged hydrogens in water and separating them from the crystal lattice. This is what we would call dissolving. Ionic substances dissolve quite easily in water for the most part, which is another property that they tend to have. So this is an intro into ionic substances, just one of the types of substances that exist and one of the types of compounds that can exist. So coming up soon, we'll be taking a look at covalent substances and how they work. So thanks for watching, and I'll see you next time.